In this laboratory lesson, we're going to see how to create a C++ node that publishes a static transform between two frames in the TF static topic, and then we will also visualize this transform in RVs. Let's start by creating a new C++ script within the BumperBot CPP examples, and here within the include folder and within the BumperBot CPP example subfolder, let's create a new C++ header file, and let's call this one simple tf kinematics.hpp. This file is a C++ header file, and so it will contain just the declaration of the class and function that belongs to it. So in the source folder, we also need to create another file called simple tf kinematics.cpp, which instead will contain the definition, so the behavior of all the function and the initialization of the variables. In the header file, let's start by including the RCL CPP library, and from this one let's use the RCL CPP HPP, and then let's define a new class called simple tf kinematics, and so let's declare this class here, so the simple tf kinematics, and let's make it implement, so let's make it inherits from the RCL CPP node class. So basically this class here implements a ROS2 node. Among the public methods of this class, let's start by declaring its constructor, so the function that has the same name as the class itself, and this will take as input a string, and let's call it name. And then, since we want to use this class to publish a new static transform, so a new transform between two fixed reference frames in which the relative position and orientation of the two frames do not change, let's import a new library, and this is the TF2 ROS library, and from this one we want the static transform broadcaster, so this one. And now we can use it, so we can use this new library that we have imported in order to declare a new shared pointer. So let's first include also the memory module of C++, and then among the private variables of this class, so here let's declare a new shared pointer, and let's create a new shared pointer to an object of the class static transform broadcaster, so this class here which we have imported from the TF2 ROS library, and let's call this one static tf broadcaster. Then, still among the private variables of this class, let's declare the message, so the transform message that contains the transform that we want to publish in the static tf topic. The message type that is accepted by the TF and the TF static topic is called transform stamped, and is defined in a standard ROS2 library called geometry messages. So let's include also this library, the geometry messages library, and from the messages of this library let's import the transform stamped HPP. And so now we can use actually this library, so we can use the transform stamp that we have imported in order to create a new message, so the geometry message, and from the message let's create a new instance of the transform stamped message, and let's call this one static transform stamped, so like this. We are only missing the C++ include guards, so let's use it here, that if is not defined the simple tf kinematics HPP, let's define this one here, so the simple tf kinematics, and here let's use the end if. So if this is not defined, let's define it, and so this avoids that the simple tf kinematics class is declared multiple times if, for example, we import this header file in multiple scripts of our workspace. So now that we have our header file, so the one that declares the simple TF kinematics and all of its functions, here let's use the capital K, so like this, the simple TF kinematics class. Now we can move to the simple TF kinematics.cpp, in which we can define the behavior of this class, so in which we can define the behavior of all these functions and initialize all the variables. So here let's start by including, so let's include from the bumper.cpp examples the header file that we have just created, and so the simple tf kinematics.hpp. And then let's start defining the first function, so the constructor of this class. So we can copy its declaration, we can paste it here, and we can define it. Let's also set here the name of the class to inform that we are not defining a new function, but we are defining this simple tf kinematics function that is in the simple tf kinematics class. With this function, so with the constructor, the first thing that we want to do when we create a new object of the simple tf kinematics class is to initialize its base class. So to call the constructor of the node class from which the simple tf kinematics is inheriting. This constructor takes as input a string, which is the name that we want to give to the node, and so let's set this one equal to the name variable. Now, within the body of the constructor, we can start using the static transform broadcaster that we have declared in the header file. But before starting using it, let's initialize this shared pointer. So this is the static tf broadcaster, and let's initialize it with the function make shared from the C++ standard library, and we want to initialize it. So let's use the parentheses as well, and this is an object of type TF2 ROS static transform broadcaster, and the constructor of this class takes as input the current object, so the current class, which we can access with this pointer, so like this. Finally, once we have our static transform broadcaster initialized, we can create the static transform message, so actually we can start initializing the field of this message. Let's start with the static transform stamp, and let's start with the header, and here we can add the information about the time when this transform has been generated. And so in the header, let's access to the timestamp, and here, in order to set the current ROS2 time, we can use the function getClock, which we have inherited. So here is get_clock, which we have inherited from the node class. And from this one, let's take the current timestamp. So let's take the now. Then we can also use the static transform stamped message, so this one here, to define the two frames that are connected by this transform. A transform always has a parent, so the first link, and also it has a child, that is the second link, which is connected to the parent. Let's start by defining the parent. So this is in the header, and this in the frame ID. So here we can set a name for the parent of this connection, and let's call it bumperbot base. And then we can also set the child, so still in the static transform stamped, let's set the child frame ID, and let's set this one to be the bumperbot top. So these two, the bumperbot base and the bumperbot top, will be the two frames that will be connected by the transform. Now that we have the two frames that are connected by this static transform, we can also define the characteristics of this connection, and so we can define which is the rotation matrix and the translation vector between these two reference frames. Let's start with the translation vector. So the static transform stamped, let's access to the transform and then to the translation, and let's set a value for x. Then let's also set a value for the translation along the y, and another for the translation along the z-axis. Let's set the translation along the x-axis to be 0, the same for the one along the y-axis, and instead let's set to 0.3, so to 30 centimeters, the translation along the z-axis. And so this means that the bumperbot top will be translated along the z-axis of 30 centimeters with respect to the bumperbot base frame. After having defined the translation, let's also define the rotation between these two frames. However, in ROS2 and in general in computer science, instead of rotation matrices, and so instead of Euler quaternions that we have seen so far, it is used the quaternion to express the orientation of an object. This representation with quaternion has several advantages compared to the rotation matrices that we will investigate later in this course. For the scope of this lesson, you just need to know that the quaternion is composed of 4 components, and so in the static transform stamped, if we access to the transformation matrix and to the rotation, we can see that there are 4 components. So the X, this one, then we have the Y component, then we have the Z component, and finally the W component. Using this tool, so using the quaternion, we can represent an empty rotation. So basically we can represent that the bumperbot top is oriented the same way as the bumperbot base frame by setting all the elements of the quaternion to 0. So the Y, the Z, and instead just the W to 1. So with this quaternion, basically we are saying that these two frames have the same orientation. Now, with this, the transform stamped message, so the static transform stamped message, is completed, and now we can finally publish it within the TF static topic. And to do so, we can use the static TF broadcaster object that we have created. And on this one, let's call the function send transform, so this function here. And this one receives as input the static transform stamped message that we have just created with the transform between these two frames. Now, once we have sent this transform into the TF static topic, let's also print a message in the terminal with the RCL CPP info string function. Here let's get the logger, so the current node scope, and let's print the message publishing static transform between. And now we can print the frame ID, so from the static transform stamped, from the header, let's print the frame ID, and then let's also print, still from the static transform stamped, the child frame ID. So we are going to publish this message here in the terminal when we publish this static transform here. For the moment, this is all we need for the simple TF kinematics class, and this is now able to send a static transform within the TF static topic. Now let's define the main function that will be executed at the startup of this node. And within this function, let's start by initializing the ROS2 interface with the init function, which takes as input the arguments of the main, and then let's also create a new instance, so a new object of this class here, so of the simple TF kinematics. Let's call this one node, and let's initialize it with the make shared function, and this is an object of type simple TF kinematics. And if you remember, the constructor of this class takes as input a string, which is the name of the node, and let's call it simple TF kinematics like this. Now, with this we have called the constructor, so let's keep this function, so let's keep this node up and running with the RCL CPP spin function, and let's make spin the node, so let's keep the node spinning. Then, if for example we stop the execution of this node with Ctrl+C, let's shut down the ROS2 interface with RCL CPP shutdown, this function here. Now, moving on, we can install this file here, so we can install this executable. So back in the cmakelist.txt, here, since in our simple TF kinematics we have used the dependencies from the TF2 rows and the geometry messages, we need also to add these dependencies here. So let's find package geometry messages, and also let's find the other package that is the TF2 rows package. Then we can add the new executable. Actually, we can copy the same line that we used for the simple turtle sim kinematics. Let's change the name of the executable into simple TF kinematics, and this is referred to the file that is in the source folder and that is called simple tf kinematics.cpp. And let's also add the dependencies to the simple tf kinematics, which are the rclcpp library, the tf2 rows library, and the geometry messages library. Also, don't forget to include this one here, so this executable, in the install list. So this one, where we have installed all the other nodes that belong to this package. We can save this file, and before running it, actually we need to include also the dependencies that we have used in the package.xml. So here let's add a new dependencies from the tf2 rows package, and then let's also add another dependency from the geometry messages, and that's all we need. Now we can start the execution of this script and see how it works. So in a new terminal, let's go to the workspace and let's build it to compile also the new node that we have declared. Then in a new window of the terminal, let's source the file setup.bash that is in the install folder, and let's start our node with rows2 run, and from the bumper.cpp examples, let's start the simple tf kinematics node. So let's press enter, and as soon as we do so, we see that this node is printing in the terminal, publishing static transform between bumperbot base and bumperbot top. So this was the frame ID, the parent, and this is the child. Actually, we can see that this node is successfully publishing this transform by taking a look at the topics that are now available in rows2 with rows2 topic list, and now we can see that actually the tf static topic is there, so is available, and you can also read its content with rows2 topic echo on the tf static, and we receive exactly the message that we published with our tf example node, and so the transform between the bumperbot base and the bumperbot top frames. And also here we can see the transformation matrix with at 0 rotation, and here this is the translation vector. We can also see this same message, so this same transform in rvis2, and so if we open a new terminal and we start rvis2 simply with the command rvis2, now in this window we can see that we have an error, and the error is due to the fact that the frame map doesn't exist, so we haven't published any frame with this name. So let's change the fixed frame with the bumperbot base frame, that is the one that we have defined and is the parent of our connection. So let's press enter. Now the error is disappeared, and actually we can add a new plugin, and let's add the TF plugin to display the frames. And here, as we add this plugin, we can already see that we have 2 frames. Also we can display the names with show names, yes, and now we have the bumperbot base and the bumperbot top. And so we can see that this transformation, so these 2 frames are connected, and they are oriented the same way, as we said that the relative orientation is 0, and also we can see that the bumperbot top frame is not translated along the x-axis, is not translated along the y-axis, and is instead translated just along the z-axis of 30 centimeters, so like this.